Good morning everyone. So today we are going to discuss the last section of inclusion exclusion principle, or we can say an application of inclusion exclusion principle. So in this we will use the principle of inclusion exclusion for solving some problem which is related to restricted arrangement. So we call it derangement. So consider the permutation of the set 1 to n numbers are there. So we call it an arrangement if, for example, there could be many arrangement. If I write 1 3 2 5 7 4 6, it is an arrangement of 7 numbers. So this arrangement, or any arrangement, we call derangement if none of the n integers appear in their natural position. For example, if I see only 1 2 3, so this is one arrangement, but if I write 2 3 1, so here the position of 1 is this, so 1 is not its position, 2 is not in its position, and 3 is not in position. So 2 3 1 is an derangement of the set 1 2 3. So we denote derangement of n objects by dn and use the principle of inclusion exclusion to find the formula for dn. So this is a table. You can see that D3 is 2 because these are the only two possibilities for derangement. D4 is 9. So let's see this problem. What is the probability if n people randomly reach into a dark closet to retrieve their hats? No person, such that no person will pick his own hat. So no person will pick his own hat. It means AI bar is ith person do not get his hat. It means AI is ith person get his hat. Yes. Now U is all the number of the ways to distribute the hats to the n people. So for example, the first person has n choices. He can get any of the hat, either his hat or some other hat, doesn't matter. And the second one, it has n minus 1 choices, and so on. So U, or n of U, or capital N, is n factorial. Now I have to consider n of AI. So if I have to consider n of AI, it means ith person get his hat. So he is done. The remaining person are n minus 1. They can either get his hat, do not get his hat. So each one, the first one has n minus 1 choices, the second one has n minus 2 choices, and so on. And of course there is no repetition, because once you get a hat, you cannot get the another hat. That's why it is n minus 1 factorial. Similarly, n of ni nj is n minus 2 factorial, and so on. So it means if I compute n of a1 bar, a2 bar, and an bar, it would be n factorial minus nc1 and minus 1 factorial, and it goes on minus 1 raised to the power k, nck n minus k factorial, and so on. Yes, where the last term is minus 1 raised to the power n and ncn and 0 factorial. Now nck and n minus k factorial is n factorial, n minus k factorial, and then n minus k factorial, and k factorial is also there. So n minus k factorial would out. It means I can write it as n factorial and then minus 1 raised to the power k by k factorial. So this is my n of a1 bar, a2 bar, and an bar. Yes, because nck transformed into n factorial by k factorial. Summation is from k from 0 to n, that's why I took n factorial out. And if I have to compute the probability, then I divide it by n factorial. So it is simply minus 1 raised to the power k by k factorial, because I am looking for the probability. But derangement which I got, I will explain why it is in derangement. But Using inclusion exclusion principle, got n of a1 bar, a2 bar, an bar is n factorial summation k from 0 to n minus 1 raised to the power k by k factorial. So the problem is equivalent to asking for all permutation of sequence 1 to n such that no number is fixed, because no one is getting its hat. It means no number is still in the ith position. This is the derangement, and we got its formula as n factorial summation minus 1 raised to the power k by k factorial. So let's see a problem. A professor has typed 5 letters to 5 different persons and also has addressed 5 different envelopes. At the end, he by chance stuffs the 5 letter into 5 envelopes at random. What is the probability no letter is stuffed into the right envelope? No letter is. So no one is getting the right position. It means I just need to find D5. I can leave the answer in this form also, or I can compute D5 also. So if you compute it, it comes out to be 44, and that's why the probability is divided by n factorial, here 5 factorial, so that's why 44 by 120. There are 7 different pairs of gloves in a drawer. When 7 children go out to play, each selects a left hand glove and right hand glove. Yes, so each one has one left, one right. In how many ways can the selection be made so that no child selects a matching? So no child selects a correct left and correct right. Yes, now to address this problem, think over it. It's a very interesting problem. So when a child he can pick, let's say all of them first pick the left glove, because then the right should be the matched. So left has no restriction. So first one has 7 choices, the second one has 6 because one has been picked. So for the left one, 7 factorial choices are there. Yes, and now the right, we do not want that a matching should happen, so therefore it would be D7. So this is A. Selection be made so that exactly one child selects a matching pair. Exactly one child now. Yes. So for the left one, it remains 7 factorial. Now we do not know which child selects a matching pair, because there are 7 childs. So out of 7, one selects a matching pair, and then for the remaining one, we don't want a matching, so therefore D6. And the last one is how to make the selection so that at least 2 children select matching pair. At least 2. It means at most 1. So at most 1 means out of the total, I have to subtract the cases A and B. So for the left hand, it remains 7 factorial. And now for the right hand, total is 7 factorial minus no child and then exactly 1. So minus D, because this 7 factorial in both the cases is for the left hand. So that's why I have already taken 7 factorial outside. So D7 minus 7 D6 is the required answer. So that's all from today's class. Thank you very much.